Okay, good morning all. Can you hear me?
Yes, sir.
Okay,
Good
thank you.
morning, sir.
Yeah, good morning. Thank you all. Just I'll summarize. So just you can go through in the Google Classroom. I've shared one first class note. So after today's class gets over, I'll be sharing the second class note. Just I am summarizing whatever I have discussed in the previous classes corresponding to the analytic function. Then I'll be continuing today's topic. So in the last class, I have discussed the concept of analytic function. So if just let me summarize it. After that, if you have any kind of doubts, you could ask me. Then I'll just try to clarify that thing. Then only I'll proceed further to harmonic functions. So what is the analytic function? So just I have told in the last class also, analytic function is much broader concept compared to the differentiability of a function, because for a function of one real variable or two real variable, if a function is given to you and you are asked to check whether this given function is differentiable or not in a given set, then it is not possible for you to answer whether the function is differentiable in the entire set or not without checking the point-wise differentiability, because differentiability of a function indicates that or identifies whether the function is differentiable at a given point or not. So a set must have more than one point, so we need to check at each and every point in the given set, and from that only we can conclude whether the given function is differentiable in the entire set or not. So without point-wise checking, we can't say whether the function is differentiable or not. Okay. But in the case of analytic function that we have already studied in the function of complex variable, we can do so. So this is much broader concept as I have told earlier also. So what do you mean by the analytic function? Analytic function, there are three kinds of analytic function. So firstly, we have studied the analytic function in a given point. So if a function is analytic in a given point, that indicates that the function is not only differentiable at that point, but also the function is differentiable in any arbitrary neighborhood that we could construct around that given point. That means it is not only differentiable at that point, but at each and every point inside the neighborhood that we can frame arbitrarily, the function will be differentiable. So it ensures us the differentiability of a function in the entire set of that is the neighborhood around the given point. And compared to this, if we want to construct if we want to identify much broader concept, that is the analytic function in a domain. That means analytic function in a point means only around that point we can construct the neighborhoods where the function will be differentiable. An analytic function in a domain means in a domain there can be more than one point. So it at each and every point inside that domain the function is analytic. That means if I pick arbitrarily a point in the domain, then corresponding to that point I can construct a neighborhood and the function will be differentiable in the neighborhood. So there are lots of points in that domain. So corresponding to each and every point we can construct a neighborhood. So we are getting a huge set where we can confirm that the function will be differentiable. We can verify whether the function is differentiable or not. After that, there are much broader concept compared to this second one, that is called the entire function. Entire function means we are not only picking up a point, we are not only confined within a given domain, rather we are considering the entire complex plane. That means in the entire complex plane, if we pick any complex number, then corresponding to this complex number we can construct a neighborhood around that point where the function is differentiable. That means the function is differentiable in the entire complex plane. So in the last class also I have studied, we have studied actually what is the criteria to check whether a given function is analytic or not. Since we are not checking the differentiability point wise, rather by considering the concept of analytic function, we are checking the differentiability in the entire set. So we need to identify, or we need to study what are the conditions. If that are satisfied, then only the function will be analytic. So I have discussed in the last class that if a function is analytic, then the function fz, let us consider a complex valued function fz where the real part is u and imaginary part is v. So if del u del x equals to del v del y and del u del y equals to minus del v del x, then we say that the function is satisfying the Cauchy-Riemann equation. So a function has to be analytic. For a function to be analytic, the real and imaginary part of the function u and v must be satisfying the Cauchy-Riemann equation, as well as all the four partial derivatives del u del x, del u del y, del v del x, del v del y must
Hello,
be.
sir.
Yeah.
Sir, are you sharing any PPT because it is not showing?
No, I am not sharing. Just I am discussing, because I have already discussed in the last
Okay.
class. I am
Okay,
summarizing.
sir. Okay.
Yeah. So then, mm, okay. So if a function arbitrarily is given fz, where real part is u and imaginary part is v, if they satisfies the Cauchy-Riemann equation as well as the four partial derivatives are continuous, then only we can say that the function is analytic, and vice versa also. That means if for a function, arbitrary function fz, these two conditions are satisfied, the function will be analytic, as well as if the function is analytic, then all these two conditions will be followed, obviously. So I have discussed two examples in the last class also, where in the first example I have shown that the function is analytic as it is satisfying the two conditions. So if out of these two conditions anyone is not satisfied, then the function will not be analytic. So that is also I have discussed in the last class. I have shown in example that the function is satisfying the Cauchy-Riemann equation at origin, but since the function the four partial derivatives are not continuous, that's why the function is not analytic actually. Okay. So let me share my screen. So do you have any kind of doubts? Up to that I have discussed in the last class. So after these things, if you have any kind of doubts or queries, you could ask me. Do you have any doubts or queries? Anupam, have you understood everything?
Yes, sir.
Umang, have you understood?
Yes, sir. Yes,
Okay.
sir.
Okay. And I'm asking everyone, Aritro, Rupam,
Yes, sir.
everyone.
Yes, sir.
Okay. Just let me share the screen. Can you see the blank screen? Can you see the blank screen?
Yes, sir. Yes.
Okay.
Yes, sir.
So that means there are two kind of things. The fz, whenever we are considering fz as u plus iv, then both u and v are the functions of x and y. That means we can write this in the form of uxy plus ivxy. That means real part is a function of xy, imaginary part is a function of xy. So if this function is analytic, then these conditions will be followed. Similarly, if these two conditions are followed, then the function will be analytic. So number one is del u del x. We can write down del u del x in the form of u suffix x equals to del v del y, and del u del y equals to minus del v del x. So that is defined as vy, this is defined as u suffix y, and this is defined as v suffix x. And number two, all del u del x, del v del y, del u del y, del v del x, this should be continuous. So if these two conditions are satisfied, then the function will be analytic. Similarly, if the function is analytic, then obviously these two conditions will be followed. Okay, so I have given the examples also. So here we will be studying one more concept of one more type of function, that is called as the harmonic function. You don't need to write it down, just I will be sharing the PPT in the Google Classroom. Just without showing the PPT, just I am writing over here, because then you will be able to understand, because if I discuss something in PPT, you may not understand. So I am writing down, that's why, so that you could understand it very easily. So what is the harmonic function? So harmonic function is not only is not applicable on the entire complex valued function, rather it is applicable on a function of two real variable. So a function of two real variable fxy is said to be analytic, said to be harmonic if you know that while we are actually considering a function of two variables, since there are two variables, we can differentiate this with respect to x and y. So we will be getting two partial derivatives up to first order, that is del f del x, and that will be del f del y. Now if I consider, let's say, a function, say fxy as x square y. So here del f del x will be equals to 2xy. So again del f del x are the functions of x and y, and del f del y will also be functions of x and y. So since they are also functions of x and y, so here also we can differentiate this with respect to x and with respect to y. Here also we can differentiate this with respect to x and with respect to y. So there will be four partial derivatives up to second order. So unlike the function of one real variable, here there will be four partial derivatives up to second order. So if I differentiate this with respect to x, what will get? Can anyone tell me what will get? If I differentiate del f del x with respect to x again, what will get?
2y.
Sorry, I can't hear you properly.
2y.
2y. Oh yeah, here I'll get 2y, but in general, if I differentiate del f del x with respect to x again, then what is the terminology? What is the notation?
d2f dx square.
Yeah, d2f not dx square, d2f dx2, not square actually. And del 2f, rather d2f not, it will be del 2f since we are considering here the partial derivative. And here, if I differentiate this with respect to y, what will get here?
Del 2f del y2.
Not del y2, this is del f del x, already del f del x is given, that means we are
Oh, then
differentiating
del x del y.
del y del x. So the last difference, the last variable with respect to which we are differentiating will come first. So del 2f del y del x. Similarly here, if I differentiate this with respect to x, we will be getting del 2f del x del y, and here we will be getting del 2f del y2. So these are four partial derivatives. So these two are called as the mixed partial derivative, since here we are differentiating this first with respect to x, then with respect to y. So just I am saying one thing here. So the mixed partial derivatives will not be always equal. That means you have studied this in first semester also. Del 2f del y del x and del 2f del x del y will not be always equal. So there is a condition. If it is satisfied, then only these two will be equal. So can anyone tell me what is the condition for which these two will be equal? Otherwise, in most of the cases, this will be unequal. But if one condition is satisfied, then only it will be equal. So anyone, can you tell me what is the condition? You have shown this in first semester. In different problems, you have shown that they are not equal, they are unequal. You have shown this through different examples.
So if they're path independent.
No path independent actually. So here there is no concept path dependent will be only applicable whenever we will be considering the limit. But in case of derivative, have you studied this? Can you remember whether you have studied, the teacher who has taken the classes has discussed this, or you have forgot? This has been discussed, but you have forgot. That can be one thing. Or the second thing can be it has not been discussed. So what is the case?
That it was discussed.
Okay. So just remember, I am telling. So these two will be equal if the partial derivatives up to first order which we are getting, that means del f del x, del f del y. If these two are continuous, then this will be equal. If these two are not continuous, then these two will not be equal. Okay. So for these two mixed partial derivatives will be continuous if provided the first order partial derivatives both are continuous, then only these two will be equal. And if these two are not continuous, then this will not be equal. Okay. Is that clear? So just I am not discussing the detailed proof. If you wish to know the detailed proof, you can contact me. But you can remember this. So this, if these two are continuous, then only two mixed partial derivatives will be equal. Otherwise, they will be unequal. Clear?
Yes, sir.
Okay. Then what is the condition for a function has to be analytic? So the function of two real variables fxy is said to be harmonic if del 2f del x2 plus del 2f del y2 equals to 0. So if the sum of two partial derivatives up to second order with respect to not mixed partial derivative, the first we need to differentiate the given function with respect to x twice. We need to differentiate the given function f with respect to y twice. We will be adding them. If both are giving us the value 0, then only the function fxy is said to be harmonic. So just I am giving one example. Let us consider a function of two variable as say x square minus y square. And what will be del f del x? What will be del f del x?
2x,
2x.
2x,
Del f del y
2y,
minus 2y, not 2y, minus
minus
2y.
2, minus
Yeah, then del 2f del x 2, 2, and
2,
del 2f del y 2,
minus 2.
minus 2. So if we add them, this will be 0. Del 2f del x 2 plus del 2f del y 2, this is 0. So that's why this function is harmonic. But if I give you the function fxy as x square y square, then what is del f del x? 2x y square. Del f del y is 2y x square. Del 2f del x 2, 2y square. Del 2f del y 2, 2x square. So sum of these two is not 0. So that's why this function will not be a harmonic function. Is that clear? When the function is called as the harmonic function and when the function is called is not harmonic function. Is that clear or not?
Yes, sir, clear.
Then now what is the relationship or why we are studying harmonic function and what is the usefulness of harmonic function? So usefulness of the harmonic function is that whenever we are considering a function of complex variable fz, then there must have the real part of the function and imaginary part of the function. You know this. If I consider a function fz equals to z square, and if I put z equals to x plus iy, this will be x square minus y square plus I into 2x. So that is our u, that is our v. So always there is some real part of the function, there is some imaginary part of the function. So if a function is harmonic, or if we'll be discussing that if the function is analytic as well as the parts are harmonic, then what we will get? If we know u, that means the real part of the function, but we don't know the imaginary part. But from real part we can construct the imaginary part, as well as from imaginary part we can construct the real part, and we can construct the function. That means if the real part of a function is known, then we can easily construct the imaginary part. If the imaginary part of a function is known, we can construct the real part. Okay. So that is the usefulness of the function. So that is a beautiful thing that we can do for the function of complex variable, but we can't do this for the function of real variable. That means if the function has the real part, we can find out the imaginary part, or if the function has the imaginary part, we can find out the real part, and we can add joining them. By joining them, we can construct the given function of complex variable. Okay. Okay. Now, what is the relationship between an analytic function and a harmonic function? Because already I have told that the analytic function is applicable for a function of complex variable, and harmonic function is applicable for functions of two real variable. So what is the relationship between these two? So relationship between these two is if a function fz is analytic where fz equals to uxy ivxy. So here the real part of that function and imaginary of that function are two functions of two variables. So if a function fz is analytic where fz is this, then uxy and vxy both are harmonic functions. So if the function is analytic, then the real part as well as the imaginary part both are the harmonic functions, and vice versa. That means if u is harmonic and there exists another function v which is harmonic, then fz equals to u plus iv is analytic. The ability not to construct an analytic function, we need actually two harmonic functions. Similarly, if a function is analytic, from that we can get actually two harmonic functions. So these are the relationship between analytic function and harmonic function. That means if a function of complex variable fz is analytic, then its real part and imaginary part will be two functions of two variables, two real variables x and y. So they are both harmonic functions. Similarly, if u is harmonic, then there must exist another function v which is also harmonic. Then by combining both in the form of u plus iv, the function that we can construct will be obviously analytic. Is that clear or not? Is that clear?
Yes, sir.
So just I am giving one example. Say fz equals to z square. This is a simple example. So know that fz
Sir,
equals
sir, please show the previous line. I'm noting. I was noting.
yeah.
Hello, sir.
Yes.
Sir, if there is a question to check a function whether it is analytic or not, instead of using Cauchy-Riemann equation, we can use the harmonic function also.
Yeah,
Right?
you can use this also. Just I am coming to this actually. Okay, just I am showing it. Okay, fz equals to z square, because both are exclusive, conclusive. That means from that we can conclude this. These two are actually vice versa, necessary and sufficient condition. So just I am discussing one example. So fz equals to z square. So you can prove that this function is analytic in the entire complex term. This is an entire function, because if you use the Cauchy-Riemann equation, so its real part and imaginary part will be satisfying that. So what is the real part? So that will be the real part, and the imaginary part will be this. So that is our v, and that is our u. So you can show that this u and v will satisfy the Cauchy-Riemann equation, and all the four partial derivatives are continuous. So from that we can conclude that this function will be analytic. Okay. Now without using that tool, I can use the tool of harmonic function. If I show that u is harmonic and v is harmonic, then combining that we are getting z square. Then also from that we can say that the function z square will be harmonic, analytic function. So this is another tool to show that, or to check whether a given function is harmonic or not. So just I am assuming that this is analytic. So from that we will try to show that both of its real part and imaginary part will be harmonic functions of x and y. So how we can check? So for u already we have shown, although I am checking this once again. So uxy is equals to x square minus. So what is ux? Ux means u suffix x means del u del x. What is del u del x or u suffix x?
2x
2x. Del u del y minus 2y.
minus 2y.
Del 2u del x 2, 2, del 2u del y 2 minus 2. So uxx plus uyy equals to 0. So u is a harmonic function. Now since this is analytic, so as per the previous theorem, this v also should be harmonic. So just we need to check this for v. So what is vxy? Xy is 2x. So what is vx? Del v del x. What is del v del x?
2y
2y. Del v del y 2x. What is del 2v del x2?
2.
Not 2, del 2v del x2. So this is a function contains that which contains y. So this is constant
0,
with
0,
respect
0.
to x, because this is
0,
a function that contains y. So while we are differentiating this with respect to x again, so this is a constant term, so this will be 0, and vyy will also be 0. So here vxx plus vyy will be 0. So from here we have already checked that the function is analytic by assuming that we have shown that the real and imaginary part both are harmonic. So conversely, if we know the real part and imaginary part, and if we show that both are harmonic and all the four partial derivatives are continuous, so here 2x is continuous, minus 2y is continuous, 2y is continuous, 2x is continuous, so these are all continuous for any value of x and y, so the function will be analytic. So by using this properties of harmonic function also we can show that a function is harmonic, but in order to show that it is analytic, not only you need to show that this is harmonic, but you need also to show that all the four partial derivatives are continuous. These four are continuous, you need to show. If this is not satisfied, the real and imaginary part is harmonic, then the function will not be analytic, because a function will be analytic if both the conditions are satisfied. That means Cauchy-Riemann equation as well as this, both are satisfied. Is that clear? Is that
Yes,
clear
sir.
or not? Okay. Now I want to discuss in general. So just I have shown it for a particular example. Now in general, if the function is given fz equals to uxy xy, then we need to show that so how we can show that. So the previous example, just I have chosen one function fz equals to z square, and I've told that this function is analytic. So for that I have shown that both the real and imaginary parts are harmonic. So here in general I need to show that. So since this function is analytic, so from that whatever we'll be getting, so we'll be getting that the function is satisfying, the real and imaginary part is satisfying the Cauchy-Riemann equation. That means ux will be equals to vy and uy will be so differentiating this with respect to x. So if I differentiate this equation both sides with respect to x, what we'll get?
Zero.
Hmm?
Zero.
0. How we can get 0?
Yeah, so
ux,
it is
vy both are functions of x and y though. So it is also a function of xy, it is also a function of xy.
second order derivative of x.
So
Who is it?
what we'll get in the left hand side?
Del 2 del x.
Del to u del x2. So u xx. And what we'll be getting here? We are differentiating vy with respect to x. So I will be getting vxy. Is that clear or not? That means del to v del x del y. Del v del y is a function of x and y both. So if I differentiate this again with respect to x partially, so this will be del to v del x del y. So vxy. Is that clear?
Yes, sir.
Similarly, if I differentiate this equation with respect to y, what will get?
UYY.
Uyy
Equals to minus Vyx.
minus vy. Very good. Yeah, this one. Now these two mixed partial derivatives. So I have told that two mixed partial derivatives will not be always equal. So what is the condition that these two will be equal? So the condition is that all the four partial derivatives up to first order must be continuous. So you know that since the function fz is analytic, So these two conditions will be followed. The first of all, the all four partial derivatives must all four partial derivatives must satisfy the Cauchy-Riemann equation, as per the second condition of analyticity, the four partial derivatives must be continuous also. So since the function is analytic, so already four partial derivatives that we have obtained must be must be continuous. So that's why these two mixed partial derivatives as per the given condition I have told will be equal. So these two are equal, so uxy and uyy will be equals to 0. So that's why we can conclude that u is a harmonic function. Now to show that v is a harmonic function, so we will consider two equations of CR equation. If I differentiate this with respect to y, what we will get?
UYX.
Uyx. Very good. The right hand side,
VYY.
vyy. We are differentiating this with respect to x. Then what we will get? What we will get? Uy. This is uy. We are differentiating with respect to x. Similarly, like that,
UXY.
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 Yeah,
XY.
will be equals to minus
UXY.
vxx. So here also these two mixed partial derivatives will be equal, since these four are all continuous as the given function fz is analytic. So that's why here vyy plus vxx, that will be equals to 0. So here v and u both are harmonic. So this proof might come in the exam, so you need to remember this proof. So in general, here in that proof we have shown that if fz is analytic, then both the real part and imaginary part are harmonic. So by Cauchy-Riemann equation and using the second property of the function fz, which is required for function fz to be analytic, we have shown that both u and v are harmonic functions. Okay.
Sir, sir, we need to prove it two times, like you did.
Yeah, you need to prove it two times because we need to show that u is harmonic, v is harmonic. So for the first one, we have shown that by differentiating this with respect to x. Once we have differentiated the first equation with respect to x and second equation with respect to y, in order to show that u is harmonic, and in order to show that v is harmonic, we have differentiated the first equation with respect to y and second equation with respect to x, so that we could get vyy and vxx. In the first case, we need to differentiate in such a way that we get uxx, uyy. The second equation we need to differentiate in such a manner that we are getting vxx and vyy. Is that clear?
Yes, sir.
Now, if the function fz is analytic, then the real part and imaginary part, this will be harmonic and this will be harmonic. So here, if the function fz is analytic, then both u and v is harmonic, already we have studied. So then u is called as harmonic conjugate of v, and v is called as harmonic conjugate of u. So then in the next class I'll be studying these three cases. That means if fz is given, fz is not given, u is given, how to find v whenever u plus iv is analytic, and if v is given, how to find u whenever u plus iv is analytic. So that is called as the finding of harmonic conjugate. That means if a function fz is analytic, then the real part and imaginary part both are called as the harmonic conjugate of each other. So there are three methods. So in the next class I will be discussing how to find out the harmonic conjugates. So just I am showing it in the PPT. So this is the condition for a function to be harmonic. So I will be sharing this in the Google Classroom. So here fxy is this. So then the theorem that I have discussed, if fz equals to u plus iv, v an analytic function and all second order partial derivatives are continuous, then both u and v are harmonic functions of x and y. The proof is here. Then the converse one, that means if u is harmonic, then there exists another harmonic functions vxy such that u and v are satisfying Cauchy-Riemann equation. Then fz that we can construct by combining u and v in the form u plus iv is an analytic function. An example is given. Then how to determine the harmonic conjugate, that means if fz equals to u plus v iv is an analytic function where both u and v are conjugate functions, that means u is harmonic and v is harmonic, then if u is known, we need to determine v, and u and v are called as the harmonic conjugates of each other. Okay, so this thing I will be discussing in the next class. There are 3 methods, so by using these 3 methods I can discuss them. Is that clear? Have you understood all these things so far I have discussed? Is it clear or do you have any doubts till now?
No, sir, it's clear.
Okay, thank you. And just wait, I am sharing the link as well as exam code for today's class. So this is the code and this is the link. So just click the link and give the exam code as well as your full enrollment number and you can complete the test. So just complete the test by 12:20. So anyone amongst you just log in and tell me whether you can access it right now or not. Can you access it right now?
No, sir. Sir, it is showing not a valid time.
Sir, not a valid time.
Okay, so just you wait for 2 minutes and you can check after 12:10. Just wait, I am also waiting here.
Yes, sir, we can access it now.
Okay. Okay, thank you. Just all of you finish the class test before 12:20. Okay, thank you all for attending today's class. So have a nice day. I'm leaving.